How does a computer predict house prices? First, we assume that the independent variables and the dependent variable have a linear relationship. When there is only one independent variable, we have two axes, one for the input and one for the output. So the prediction becomes a straight line on a two-dimensional plane. If there are two independent variables, we now have three axes, and the prediction forms a plane in three-dimensional space. And as the number of independent variables increases, even though we can't visualize it anymore, the model predicts by finding a hyperplane in n-dimensional space. Now, we've already learned one equation that can represent a line, a plane, or even a hyperplane. It's written in vector form as y equals w transpose x. There are two key ideas here. The first is the model itself. A model is simply a function that takes an input vector x and produces an output y. The second are the model parameters, the weight vector w. Each element of w multiplies its corresponding component of x, which forms the dot product. So, the larger a particular wi is, the more influence its corresponding input xi has on the prediction. In short, you can think of w as a set of numbers that show how important each input is for the prediction. Let's look at an example. If there is only one independent variable, the model becomes y equals w0 plus w1 times x1, which is a straight line. Here, a larger w1 means x1 has a stronger effect, and w0 acts as a bias term. If there are two independent variables, the dot product of x and w defines a plane. Then w1 and w2 control the influence of x1 and x2 respectively. To sum up, the model is the framework, the function itself, and the parameters w are the components that adjust how much each input contributes within that framework. In machine learning, x and y are given as data. Our goal is to find the model parameters that define the model. The key idea is this. After assuming a linear relationship, we find the weight vector w that minimizes the difference between the predicted values and the actual values. In other words, the squared errors. This expression is called the sum of squared errors, or SSE. And when we divide it by the number of data points, we get the mean squared error, or MSE. Both SSE and MSE lead to the same optimal W, but MSE is more commonly used. Why? Because SSE keeps increasing as we add more data. It's always adding positive values, so the total naturally grows larger. So when we look at SSE, what can we really tell? Intuitively, not much. But when we divide by the number of data points to get MSE, we can understand how far, on average, the predicted values are from the actual values. In simple terms, MSE tells us how far our prediction line is, on average, from the actual data points. Still, as I mentioned earlier, it doesn't matter which one we use, SSE or MSE, because both will lead us to the exact same optimal model parameters, W. Now, in the MSE equation, we can rewrite y hat in terms of W. What was it again? Right, since y hat is the predicted value, it's equal to W transpose X, so we can express the loss function as L of W. This function is quadratic with respect to W, so it forms a convex bowl-shaped curve that opens upward. That means if we find the value of W where the derivative becomes 0, we can directly calculate the optimal W. You might ask, wait, W and X aren't just simple numbers, they're vectors, right? Yes, exactly. Because the product W times X gives us a single scalar value, we can think of L of W as a quadratic function of the parameters W. When we consider W as a vector, the number of parameters simply increases, and L of W becomes a multivariable quadratic function, a bowl-shaped surface in higher dimensional space. To build intuition about MSE, let's explore it as a multivariable quadratic function.
Like, comment, subscribe, and turn on notifications.
Let's look at the simplest example, a case with only one independent variable. It's the relationship between the size of a house and its price. The prediction line is written as y hat equals W transpose times x. Here, W is a column vector made up of two components. If we expand this vector expression, we get y hat equals W0 plus W1 times x1. Now, let's substitute this into the loss function L of W. We simply replace y hat with W0 plus W1 times x1. Then we can express L as a function of W0 and W1, L of WO, W1. Even in the simplest case with just one independent variable, L of W is still a multivariable polynomial. Now let's actually find the weight vector W that minimizes the MSE. We'll start with the simplest situation when there's only one data point. On our coordinate plane, we have just one data point like this. The line that minimizes MSE only needs to pass through this single point. It's any line whose predicted value y hat matches the actual value y. There are infinitely many such lines that pass through this point. Let's look at this mathematically. Since there's only one data point, the loss function becomes very simple. Because L is a squared value, to minimize it, we just need to make the expression inside the square equal to 0. If it's not 0, the square will always be positive. It's the same idea when we take partial derivatives. When we take the partial derivative with respect to W1 and also with respect to W0, the condition for them both to be 0 is exactly the same. The term inside the parentheses must be 0. Even when x equals 0, W1 becomes a free variable, so there are still infinitely many solutions. Now let's try plotting W0, W1, and the loss function L on a three-dimensional coordinate system. Will we get a nice 3D surface? Not really. We already know that L equals 0 at its minimum, and that there are infinitely many pairs of WO and W1 that make L 0. So we can already predict that all these points will lie on the WO, W1 plane where L equals 0. In fact, this equation takes the shape of a straight line. Here, x and y are given data values, while WO and W1 are the unknowns. It feels confusing, right? We're so used to thinking of x and y as unknowns, but here they're fixed values. You'll need to get comfortable flipping that perspective. Since L equals 0, let's drop the L axis altogether and just look at the line itself. This line represents the entire set of solutions, the set of WO, W1 pairs that satisfy the equation. Now, let's consider the case with two data points. What line minimizes the MSE for these 2 points? That's right. It's the line that passes through both points. There's only one line that passes through 2 points. So, the line that minimizes MSE is unique, and the minimum value of MSE is 0. Let's see this mathematically. We want to minimize the loss function, but we already know that its minimum value is 0. And each individual term is also 0. Why? Because the line passes exactly through both points. In the end, we're just solving a system of equations. The coordinates x1, y1, and x2, y2 are given data, and the unknowns are WO and W1. So we have 2 equations with 2 unknowns. You can also solve this using partial derivatives if you like. Try it out. Let's visualize this in 3 dimensions. What shape do you expect? Exactly. We already know that the line connecting the 2 points minimizes MSE. So if we solve the system of equations for WO and W1, The solution is just a single point in the WOW1 plane. Now let's look at the case with 3 data points. Is there a line that passes through all 3 points? No. Unless the points are perfectly collinear, it's impossible for one line to pass through all 3. So, as you can see in the animation, the sum of all the squared errors cannot be 0. The same goes for 4, 5, or more points. Now we want to draw the line that minimizes the errors. Unlike before, the loss function L is not 0. So to draw this red line, we need to find the values of W0 and W1 that minimize the errors using a different principle. What principle is that? Let's see. The loss function L is the sum of 3 squared terms, and none of these terms can be guaranteed to be 0 because the points are not on the same line. We can write this more generally. We sum the squared errors for all 3 points. This should look familiar. It's exactly the SSE formula. And if we divide by the number of data points, we get MSE. Now let's plot the loss function L with respect to W. Does the shape look as expected? In reality, the original data can produce a very extreme shape, but I normalized the data to make a nice, understandable bowl shape. The red point on the graph represents the coordinates of W0 and W1 that minimize the MSE. The L value at that point is the minimum MSE. And with these values of W0 and W1, we can construct a line that best fits the data. We can also see that the MSE function, expressed in terms of W0 and W1, is convex, just like a simple one-variable quadratic function. What does this mean? By taking partial derivatives with respect to W0 and W1 and setting them to 0, we find the slope and intercept of the line that minimizes the MSE. Now let's solve for W using partial derivatives. First, we take the derivative with respect to W0, and then with respect to W1. For both equations, we can multiply both sides by 1/2 to simplify, removing the factor of 2. And for convenience, we'll omit the lower and upper limits of the summation. At this point, since xi and yi are just the data values, you might think, I can just solve this as a system of equations. But let's go a bit further to see what intuition we can gain. Let's start with the simpler case, the partial derivative with respect to W0. We can distribute the summation over each term. Adding 3 10 times is the same as adding 1 10 times and then 2 10 times. So the distributive law holds. W0 is just added n times, giving n times W0. Then we can multiply each term by 1 over n, which you're familiar with. For W1, xi is a common factor, so we can factor it out. Now xi and yi are sums over n data points, divided by n, which gives the averages, x bar and y bar. After simplifying, the expression for W0 looks like this. Next, let's simplify the partial derivative with respect to W1. We distribute the summation over each term again, and this time xi is also part of the term, so we distribute it as well. We can factor out anything not related to the summation, then multiply each term by 1 over n as before. The sum divided by n gives the averages again. Finally, we can express the simplified formula for W1. Notice that W0 appears in the equation for W1, and W1 appears in the equation for W0. How do we solve this? We can substitute W0 into the W1 equation. It's actually easier to substitute W0 into the W1 equation. After substitution, we rearrange the terms so that W1 is on the left side, subtracting anything we need from both sides. Now W1 can be factored on the left and everything else cancels out on the right. Multiplying both sides by the reciprocal of the coefficient, we end up with the final expression for W1. Take a closer look at this formula. The numerator is essentially the covariance between x and y, and the denominator is the variance of x. Of course, there's no 1 by n-1 factor in this version, but if you expand the formula, you can see that W1 is covariance over variance. Since variance is always positive, the sign of W1 depends on the numerator. If both x and y increase together, the numerator is positive, so W1 is positive. If x increases but y decreases, the numerator is negative, so W1 is negative. This captures the fundamental property of the slope. W1 is positive when x and y change in the same direction, and negative when they change in opposite directions. Now, let's look at W0. Since we already solved W1 in terms of x and y, we can just substitute that expression into the equation for W0. It looks complicated, but we can simplify it a bit using sigma notation. Even then, it's still a bit complex, but let's go through it. If we look at the denominator, we can see that it's proportional to the variance of x. Now looking at the numerator, the first term reflects the mean of y, and the second term reflects the covariance between x and y. So what does this mean? W0 represents the average level of the dependent variable. In this example, the average house price. It sets the baseline of y based on the data, and then considering the correlation between x and y, house size and house price, it adjusts the line so that it passes through the data on average. In other words, the intercept, W0, shifts the line up or down to minimize the MSE. Let's make it more intuitive. The optimal W0 is the value that sets the partial derivative with respect to W0 to 0. If we rewrite the derivative in terms of y hat, what does it mean? Think about it. It's the average of the residuals, the errors, and it equals 0. In other words, the moment we find the optimal intercept W0 that minimizes MSE, the mean of all the prediction errors is automatically 0. Graphically, if we input the mean of x into the regression model, the predicted y hat will exactly equal the mean of y. The intercept ensures that this property holds, adjusting the regression line up or down as needed. If you reflect on this for a moment, it makes intuitive sense. Finally, let's see mathematically why the loss function L has a bowl shape. If we expand the equation and focus only on W1, the coefficient of the highest degree term, W1 squared, is the mean of x squared. Since the mean of squares is positive, the quadratic in W1 opens upward. Similarly, for W0, the coefficient of W0 squared is 1, which is also positive. So L is convex with respect to both W0 and W1. We can also check this by taking second derivatives. The second derivative of L with respect to W0 is 1, which is positive. The second derivative with respect to W1 is the mean of x squared, which is also positive. In conclusion, L of W0 and W1 forms a paraboloid in the W0-W1 space, a three-dimensional bowl that opens downward in all directions.